Hello and welcome to the very last section of the quarter. This is section 15.8 on the divergence theorem. Okay, so recall that we use the circulation form of Green's theorem to introduce Stokes' theorem. So here we're going to use the flux form of Green's theorem to introduce the divergence theorem. So let's first recall what it says, right? It says that the total flux of a two-dimensional vector field F throughout some region R in the xy plane is equal to the flux of that vector field through the boundary of the region. Okay, so to spell that out in a little more detail, first remember that this quantity del p del x plus del q del y is what we define to be the two-dimensional divergence of the vector field, and it's measuring the flux density of the field at a point. Okay, so if I take the product of the divergence and this little differential change in area, what does that tell me? Well, let's suppose that the vector field F is describing, say, the flow of a fluid that's moving throughout this region R. Well, there, the flux density times this little change in area is going to tell me the rate of flow as fluid enters in and then exits out a little neighborhood of a point in our region. And so if I sum up all of those rates of flow as we range throughout the region R, that's what this double integral on the right is doing. That's going to tell us the total rate of flow throughout the region, okay? And the flux form of Green's theorem says that that total rate of flow throughout the entire region is equal to the rate of flow across the boundary, okay? That's what this line integral on the left is doing. All right, so now let's turn to the divergence theorem. Okay, so here we have a three-dimensional solid D in R3, and its boundary S is a closed two-dimensional surface in R3. In the divergence theorem, right, this says that the total flux of a vector field throughout the solid D is equal to the flux of the vector field through the boundary of that solid. Okay, so it's essentially the same statement as the flux form of Green's theorem, it's just we're bumping things up now in dimension. Okay, and so here we have the three-dimensional divergence of the three-dimensional vector field F, and it's measuring, again, the flux density of the field at a point. And so the flux density times this little change in volume, that's going to tell me the rate of flow as fluid enters in and exits out a little neighborhood about a point in our region D. So if I sum up all of those rates of flow throughout the solid, right, that's what this triple integral on the right is doing. That's going to tell us the total flow rate throughout the solid. And the divergence theorem says that total flow rate is equal to the rate of flow across the boundary of the solid. All right, now a note here on orientation. The triple integral on the right assumes an outward orientation for the boundary surface. All right, so it in other words, is measuring outward flux, right? The rate at which fluid is exiting the solid. Okay, so if it does turn out that the boundary surface is oriented so the normal vectors are pointing inward, well then the integral on the left would actually be the opposite of this triple integral, but that's an easy fix. We can just introduce a negative. It's the same issue we saw with Green's theorem and orientation there. All right, cool. So now let's go ahead and make a few comments here about Stokes' theorem and the divergence theorem now that we've introduced both. So remember, the Stokes' theorem is really a statement about a two-dimensional surface in R3 and its boundary curve, which is one-dimensional. Okay, and it says that the total circulation of your vector field over this surface is equal to the circulation along the surface's boundary. Okay, the divergence theorem, on the other hand, is really a statement about a three-dimensional solid and its boundary, which is a closed two-dimensional surface in R3. Okay, and so we have a triple integral, right, and a surface integral here, and it's saying that the total rate of flow, in other words, the total flux throughout the solid, is equal to the rate of flow across the boundary. Okay, so now it can be a bit confusing at times to know which of these theorems is appropriate, but it's usually pretty clear as long as you are careful about just understanding what types of regions you're really dealing with and ultimately what quantities it is you are interested in computing. Okay, so we'll see all of that illustrated in the examples to come. All right, so now the last thing I want to say is just a few things about the intuition behind the divergence theorem. Okay, so let's say I have some solid that's made up of these, say, two boxes, and they have this common face here. And let's say we make the determination that if fluid is flowing out of a box, we're going to count that as positive flow, and if it's flowing into the box, we're going to count that as negative flow. Okay, so along this common boundary here, okay, this box right here, let's say the fluid is moving from left to right. Okay, this box is going to count that as positive flow, right? Because it's flowing out of this box on the left. But see, the box on the right is going to count that as negative flow. And so these rates here are actually going to cancel out along this common boundary piece. And we'll find that the net rate of flow of the vector field throughout this entire solid is in fact just equal to the rate of flow on the boundary of the solid. Okay, so now if I have a more general solid, okay, the idea is, well, just to fill out that solid with a bunch of these little boxes, right? And by the same argument, all of these internal rates of flow are going to cancel out, and the net rate of flow we'll find is just going to occur out here on the boundary. That's exactly what the divergence theorem says. Okay, it says that the net rate of flow, which is what this triple integral is measuring, is equal to the rate of flow across the boundary. All right, great. Well, we'll stop there and we'll start getting in some calculations in the next video. All right, see you there.